Hello, everyone. For the next few days, we need to take a step back from energy and learn some not-so-basic math. So let's start out by remembering some of the things that we have learned this year. Right? We know that every slope is a derivative. Right? So given a position time graph, like a top-opening parabola, right, if we want to find the velocity at some point, right, we have to find the slope of the tangent line at that point. The slope of the tangent line to a position versus time graph is the velocity, and that means we need to take a derivative of the position with respect to time. Similarly, if we have a velocity time graph and we want to find the acceleration at some time, we need to find the slope of the velocity time graph, which is itself a derivative of the velocity as a function of time, or the second derivative of the position with respect to time. And that gives us an acceleration time graph. These, of course, are the typical graphs we got for uniformly accelerated motion, as you can see here with the horizontal acceleration time graph. But even in more complex position functions, right, we can use the calculus to go from position to velocity to acceleration. Right? Evaluate them at any time, and we have those values. Right? Or the entire functions can be found by using calculus. But how would we go the other way? What if we had the acceleration function and we wanted to know the velocity, and from the velocity we wanted to know the position? Is there math that would let us do that? Good question, huh? So you might remember back when we did motion graphs and kinematics and all of that good stuff, we didn't just focus on slopes and y-intercepts. We also looked at another quantity, the area under the curve. So let us consider that for a moment. Here is our uniformly accelerated motion acceleration versus time graph, right? Nice horizontal line. Well, let's say that our object is moving from a time we will call t1 to a time we will call t2. Let's look at the area under the curve from t1 to t2. Now, we could find this rectangle right here. Okay, we have enough geometry that we could do that. But let's look at this in a little calculus-y way. We could find the area between t1 and t2 by first finding the area from 0 to t2, which would be this big rectangle, right, from 0 to t2, and then subtracting off the area from 0 to t1. With me there? So again, we could do the area from 0 to t2, and then subtract off the area from 0 to t1. And that would leave us the area in between. Well, certainly we could do those areas. I mean, they're just rectangles, right? So it's just length times width. So the area of the big rectangle is just a times the acceleration times t2. And the area of the smaller rectangle is just a times t1. But this is a uniformly accelerated motion. So we do have some kinematic equations. If we factor out the a here, then t2 minus t1 could also be written as delta t, change in time, right? Or we could write it as t. We kind of are pretty sloppy. That's one of the few notation things that we're really kind of sloppy with. We sometimes use t to mean a specific time, but we also could use t to mean an interval of time. Right? Delta t is a little more explicit. Well, if we apply the first kinematic equation here, final velocity equals the initial velocity plus acceleration times time, subtract the initial velocity to the other side, and what do we have? Final minus initial, which is change in the velocity. Then we see here that the area under the curve of the acceleration time graph tells you how much the velocity changes. Now be careful. This isn't as powerful in some ways as a derivative, right? Because it doesn't give you the velocity function. It doesn't allow you to calculate what the velocity is at t1 or what the velocity is at t2. It just tells you how much the velocity changes from t1 to t2. right? If we take the acceleration times the time, which is the rate of change of velocity times the time it's changing, we get how much the velocity changes. So this gives us at least some of the information about the next graph up, right? About the velocity time motion. Not all of the information, but some of it at this point. If we start in a velocity time graph, and we again look at, well, what's going to happen from t1 to t2? Well, on the velocity time graph, at t1, it will be moving at a velocity I shall call v1, and at t2, it shall be moving at a velocity I shall call v2. Now, we could find the area under the curve here. We could break it up maybe into a rectangle and a triangle, or use a trapezoid equation if you know that. But it's almost easier to just find the area under the curve from t1 to t2 by finding the area from 0 to t2, which is the big triangle, minus the area from 0 to t1, subtract off the little triangle, and that gives us the area in between. We know the area of the triangle. We've done that lab, right? It's 1/2 base times height. So the big triangle would have 1/2 a base of t2 and a height of v2. And our little triangle would have a base of t1 and a height of v1. So there's the 1/2 base times height for each of those triangles. That might actually be easier than doing the area of a rectangle and a triangle to find this. But again, that doesn't really tell us much until we again apply the kinematic equations. Right, remember that velocity 1 is the initial velocity plus the acceleration times t1. Right, and notice I don't, the initial velocity is the same always, and the acceleration is constant. And v2 could be calculated by taking the initial velocity plus the acceleration times t2. But what is the initial velocity? Well, in these simple cases that I've chosen, the initial velocity is 0. So those cancel out. So if we substitute in for v1 and v2, we get that those areas can be written as 1/2 t2 times the quantity acceleration times t2 minus 1/2 t1 times the quantity acceleration times t1. Take a moment before going on, or rewind, and check out my algebra, my geometry, and my uniformly accelerated kinematic equations. If we multiply those things together, we then get 1/2 a t2 squared minus 1/2 a t1 squared. But you're hopefully saying to yourself, wait a minute, I've seen that before. 1/2 the acceleration times the time squared. That's the third kinematic equation if the initial velocity is 0, which it is in this case. Remember, final minus initial displacement. Another way of writing that is displacement. So the displacement is 1/2 the acceleration times the time squared. Plug that in, and we get that the area is really the total displacement to t2 minus the displacement to t1, tells you the displacement in between t1 and t2. Right? Delta x2 minus delta x1 is the displacement to t2, and this is the displacement to t1. You subtract them. So the area under the curve from t1 to t2 is basically the displacement from t1 to t2. Hopefully not too shocking. We did a lot of those kinds of things back in the motion graph, kinematic, motion in one dimension unit. But it looks like we get these nice areas. And again, though, notice, it doesn't tell you the position function. Right? It tells you the change in the position. So it does give you some information about the next graph up, if you will, but perhaps not all of the information yet. But at least it's part of the puzzle. Now, in this case, I did uniformly accelerated motion. And in uniformly accelerated motion, the graphs were nice. It was a horizontal acceleration time graph and a diagonal linear velocity time graph. And so to find areas under the curve, you just use basic geometry. But what if the velocity, this is a velocity time graph, what if the velocity time graph was something funkier like this? Well, the same ideas hold, right? We could find the area under the curve from t1 to t2 by taking the area from 0 to T2, this big shape, and subtracting off the area from 0 to T1, that little shape, and we'd have the area in between. But how are we going to find that area when it's not a nice shape? Well, one way we could maybe approximate this is if we could try to fill in this shape with shapes of which we know how to take the area. Like, let's say, rectangles. What if we filled this shape with equal width rectangles? See what I'm doing there? Now you'll notice it's not perfect because this is curvy, right? So these rectangles are kind of overhanging a little bit. These rectangles are under a little bit. But it's an approximation. One way to get it without, getting too complex. Well, could we make this better? How could we make our approximate area closer to the actual area? What could we do to the rectangles? Maybe if we made the rectangles smaller, thinner. In other words, if we increased the number of rectangles that we use to fill the shape, like this. That took me a while to make. Right? If we increase the number of rectangles by making them thinner, smaller increments of time, right? Shrinking the time increment, then we get smaller overhangs here and smaller, empty spots here, and we're getting closer and closer to an actual good value for the area under the curve from T1 to T2. So if we wanted an even better value, we'd increase the number of rectangles. An even better value, we'd increase the number of rectangles. An even better value, we'd increase the number of rectangles. And if we wanted to do a perfect fit, we would take that number of rectangles and increase it to infinity. That in math, in pre-calc, is what we call taking the limit. So we would take the limit of the sum, it's a summation symbol, take the limit of the sum of the area of the rectangles as the number of rectangles approached infinity. And here is the number of rectangles. So the actual area under the curvy curve we have here, mathematically speaking, would be to take the limit of the sum of the area of the rectangles as we increase the number of rectangles to infinity. Now, if you're thinking, well, this kind of sounds familiar to some of the calculus we've done before, right? Before we took 2 points and shrunk the time interval in between them, right, to find the area, find the slope of the tangent line. So we're kind of doing an opposite kind of thing here, right? Note that the area of a rectangle is length times width, right? Delta y times delta x, while a slope is delta y over delta x, right? Rise over run. So we're really doing the inverse thing here, aren't we? Area under the curve as an inverse to slope. This is what is known as, in the calculus, a definite integral. Definite integral. This is the area under the curve between definite limits. Okay, so you're actually picking the 2 times and finding the area between them. Again, this doesn't give us a function, it gives us a number answer, a definite answer, if you will. Okay, so it's not quite as good as a derivative. We'll get there, but it'll take us a couple of days. Now, of course there is funky notation for this because of calculus. I'm going to have you watch a little movie that's going to talk about the battle between Newton and Leibniz to see who would get credited as the discoverer of the calculus. Right? Newton usually gets the credit, even though not sure he really should. But the notation we actually use is Leibniz's. Okay? So this is sometimes known as the fundamental theorem of calculus. Whew. This little symbol here is a stretched German S. Draw a capital S and stretch it. Right? S for kind of like it's a summation, because it's the limit of a sum of the area of the rectangles. Ooh. This is called an integral sign. okay, this stretched s. So you would read this as the integral of the function f of x with respect to x evaluated from t1 to t2. I know, there's a lot going on in these, right? It's harder than derivatives. It's usually why we wait till second semester to do these in calculus, right? And why I waited till now to do these instead of trying to throw them all in with the other calc. So again, this is the integral of the function with respect to x. You need to write the dx because that tells you what's on your, basically what's on your horizontal axis, okay? Evaluated between our definite limits, t1 to t2. T1 is what's known as the lower limit, because it's smaller, right? T2 is what's known as the upper limit, because when we read a graph, right, we go from small to large, reading from left to right. So this is the lower limit to the upper limit. And you always evaluate it by taking the function we're going to get and evaluating it at T2, which is the big rectangle, or sorry, the big shape, and subtracting off, evaluating it at T1, which is the little shape, right? And then you get the area in between. Okay, now I want you to really think about that, because this is something that, you know, I have a couple of degrees in physics, but as an undergrad, I had a physics major and a math minor. So I did countless integrals, both in physics and just straight math, right? But I'm not sure I really understood the fundamental theorem of calculus until I was teaching APC the first time. And I got to about this point. Of course, this is when I was drawing diagrams on a chalkboard. And I started laughing, and the students asked me why I was laughing. And I said, because I understand why an integral is done this way. Right? Why do you always evaluate at the upper limit and then subtract off evaluating at the lower limit? Because what you are literally doing graphically is finding the area of the big shape, subtracting off the area of the little shape, and ending up with the area in between. If you keep that in mind, kind of like every time you take a derivative, you're finding the slope, which is a rate of change of two things. How much does one variable change when you change the other? Right? You'll understand what a derivative will tell you. Well, if you remember this, you'll have a better idea of what an integral is doing, what it looks like graphically, and how to do it. Now the question then is, well, how do we actually do the calculus, right? So unfortunately, this is going to take some rules. Kind of like with the derivative rules, I am not going to prove them to you, right? I'm just going to give them to you, and we're going to use them. You will spend most of second semester calculus learning why these are the rules and how to use them on functions that are way more complex than we're going to look at, okay? So, in terms of me writing the rules, anytime I write an A, B, G, E, M, or N, they're constants. Our variables are going to be X and Y because I'm going to give you the math rules, all right? And then we'll apply them to specific situations in physics. So I'm going to write out the differentiation formula, the derivative formula, and then the integration formula, the integral formula, because they're related to one another, right? Because we're kind of doing the inverse thing, right? We're going down the graphs with derivatives and up the graphs with integration. So let's start out with if we had a function y equals a to the x. Well, we know that the derivative of y with respect to x, right, the derivative of ax with respect to x would just be a. Remember, to do a derivative, you subtract one from the exponent, and then you subtract one from the exponent and divide by the new exponent. I'm sorry, you subtract one from the exponent and divide by the exponent. Oof. So dividing by 1 is 1, right? And then subtracting 1, you get x to the 1 minus 1, which is x to the 0, which is a 1. So you get a. Sorry. Integration. Let's go backwards. The inverse, if you will. What if we have a constant function, y equals a, and a is just a constant? What would the integral of that be? Okay, well, okay, the integral of y with respect to x, evaluated from e to g, and I don't really care about these limits of integration here, I'm just writing them in for the formula, okay, is the integral of a with respect to x from e to g, because I'm plugging in the formula. Right? And kind of look at these. If the derivative of ax is a, then what would the integral of a with respect to x be? Yeah, it would be the inverse. It would be ax, right? Evaluated from e to g. We would evaluate this at g, minus evaluating it at e. Big area minus the little area is the area in between. See how these are inverses? If the derivative of ax is a, then the integral of a with respect to x is ax. Well, then let's do the super important power rule. Right? So for derivatives, if we have a function y equals x to the n, remember n is a constant, then the derivative of x to the n with respect to x is n times x to the n minus 1. Multiply by the exponent, subtract 1 from the exponent. I know, I kind of messed that up here, didn't I? Multiply by the exponent, subtract 1 from the exponent. Sorry about that. I was thinking integrals. So what are we going to do up here then? Right? What if we have y equals x to the n and we want to take the integral of y with respect to x? So the integral of x to the n dx. Well, if here we subtract 1, then what do you think we'll do here? Yeah, we'll do the inverse. We'll add 1. And instead of multiplying by the original exponent, we're going to divide by the new exponent. So in words, you'll hear me say this a bunch, right? To take an integral, you add 1 to the exponent, divide by the new exponent. I know, we're going to do some examples. Derivatives, multiply by the exponent, subtract 1 from the exponent. Integrals, add 1 to the exponent, divide by the new exponent. We'll see how this works. Now, other than that, the other kind of rules we know work the same in differentiation as they do in integration. Right? If we have a constant out front, ax to the n, we can factor that constant out front and take the derivative of what's left. We can do the same thing with integration. If we have a function y equals ax to the n, and we want to take the integral of y with respect to x, which is the integral of ax to the n with respect to x, evaluated from e to g, we can factor out the constant and then just take the integral. And the integral would be the power rule, add 1 to the exponent, divide by the new exponent. So this is the power rule with a constant, right? So if you remember this one, this will get you through most of the integrals that we do in here. Right? So that's a big one. So really the constant just comes along for the ride, yeah? Sum or difference, right? The derivative of a sum or a difference is the sum or difference of the derivatives. Right? So the derivative of ax to the n plus or minus bx to the m, n and m are different constants, because otherwise you could put the terms together, they'd be like terms. So we could take the derivative of ax to the n plus or minus the derivative of bx to the m. The derivative of a sum or difference is the sum or difference of the derivatives. And just to go through the rest of it, we can factor out the a and the b and then take the multiply by the exponent, subtract 1 from the exponent. On the other hand, same formula, function if you will, but this time if we're going to integrate it and evaluate from e to g, we can again say that the integral of a sum or a difference is the sum of the integrals, sum or difference of the integrals. The integral of a sum or a difference is the sum or the difference of the integrals. And in each case, we could factor out the a and the b and then take the integral of what's inside, which is add 1 to the exponent, divide by the new exponent. Evaluate it at the upper limit, minus evaluating it at the lower limit. Big shape minus little shape gives you the area in between. So let's do some examples, okay? And as I like to do here, we're going to do some examples where we're going to be able to do these things geometrically on the graphs, and then we're also going to do them with calculus to show you that the calculus rules that I just taught you make the same prediction as the graphs do. So say we have a fairly straightforward function here, velocity function, of 4 meters per second squared t plus 1 meter per second. Okay, so it's basically v equals 4t plus 1. Okay, I want to know what the object's displacement is from 0 to 1 second. Notice I don't want to know what its velocity is at 0 or at 1 second. I want to know how much did the position change from 0 to 1 second, right? Well, first off, let's make a graph, okay? Since it's just a t and not a t squared or square root of t or anything funkier, right? This is a linear function of time, and it has a y-intercept of 1 and a slope of 4. So it should look like that. Hope you're okay with that, right? Here's a y-intercept of 1 after 4 seconds. Right? It's 4 times 4 is 16 plus 1 is 17. Right? So that's a slope of 4. Are you okay with that? Feel free to pause and sketch your graph. So method 1 to find the object's displacement from 0 to 1 second, right, is to find that area under the curve from 0 to 1 second. And that would be the area from 0 to 1, which is that area. Okay, that's really all we have here, right? We don't have an area to subtract off because we're going from 0. Right? 0 is our lower limit, if you will. So it's this, which you notice I broke up into a rectangle and a triangle. Rectangle is length times width. Triangle is 1/2 base times height, which I hope you're okay with that. Right? And that's 1 for 1 second, 1 meter per second for 1 second. This is, notice that's 5. So the height of this triangle is 4 meters per second for 1 second times a half because it's a triangle. 1 times 1 is 1 meter. 1 times 1 times 4 is 2 meters. When you add those up, you get 3 meters. Are you okay with that? So that's the kind of geometric way of figuring out the displacement. Again, I don't know where it started from. I don't know where it ended. But I do know that in the first second, it went 3 meters. And since it's positive, it means it went to the right 3 meters if we're doing one-dimensional motion here. Right? So it just tells me how much the position changes. Now, in this case, it's almost overkill, but we could do the calculus. Saying I want to know the object's displacement from 0 to 1 second is the same as saying I want to know the integral of the velocity function with respect to time from 0 to 1 second. See how I mapped those lower and upper limits onto the integral? Okay, the integral of the velocity with respect to time is the displacement, right? So if we plug our function in, I'm going to write out lots of steps because it's the first one we did. So this is the integral of a sum. So that's the sum of the integrals. Note here, please, don't lose the dt. Those of you that have had a year of calculus, right, will probably understand this, that it's an easy point to lose on a test when you don't write the dt. That's telling you what's on your x-axis, your horizontal axis, if you will. It's really important, right? It's what are we integrating with respect to. So you got to have that dt. It's part of the language. It's Leibniz's notation. So let's do these integrals here one at a time. Okay, 4t, we add 1 to the exponent, and we divide by the new exponent. Right? Add 1 to the exponent, divide by the new exponent. That's 1 plus 1, right? Over here, we add 1 to the exponent, but you might say, well, there isn't an exponent there, but there is. It's a t to the 0. Right? T to the 0 is 1. So we add 1 to the exponent, divide by the new exponent, or we just use the constant rule that we saw a moment ago. 4 over 2 is 2. 1 plus 1 is 2. Right? So this is 2t squared plus t. Now we're not done yet because we actually haven't evaluated the areas. Right? We've got to evaluate it from the upper limit minus the lower limit. But I want you to notice something here. If you're not sure if you did the integral right, take a derivative. See what you get back. You're probably much better than that at this point, I hope. What's the integral of 2t squared? Yeah, it's 4t. What's the integral of t? 1. We get the function back. Always a good thing to remember to help you check your integrals. right? You can always take a derivative of your function that you get, and you should get the original function back because they're inverses of one another. So we have to evaluate this at 1, plug in 1s for the t's, don't forget squared, and then we have to subtract, evaluating it at 0, but it just ends up being 0 because there isn't an extra little triangle to subtract off. 2 times 1 squared, 1 squared is 1, times 2 is 2, plus 1 is 3. Now, you might look at this and say, well, that was way more complex. And I suppose it was, right? But if you really know how to do integrals, those of you that have had a year of calc, right, would probably step from this step almost like right down to here to the answer pretty quick, right? You get better at them. And certainly the more complex the function, the more useful the calculus is going to be. Let me show you what I mean. Part B. What is the object's displacement from 2 seconds to 4 seconds? Okay, method 1, we're going to grind through the geometry of the situation. It's the area under the velocity time graph from 2 to 3 seconds, which we could calculously write as the area from 0 to 4. Hang on. Don't know why I did that. I spent all this time making this beautiful thing. The area from 0 to 4 minus the area from 0 to 2. You with me? And that's the area between 2 and 4. Well, you can find those areas. It's rectangles and triangles. Here they are. If you want to stop for a moment and pause and work through the geometry, go ahead, but I have faith that you can do it. You calculate it all out, you should get 26 meters. That's how far it goes to the right, from 2 to 4 seconds. Again, not where it was at 2, not where it was at 4, but how much its position changed from 2 to 4. Okay? A little trickier with the geometry here. Lots of rectangles and triangles. Method 2, let's do the calculus. This would be the integral of the velocity with respect to time evaluated from 2 to 4 seconds. Well, the function is 4t plus 1. If we take the integral of that, we already know what the integral is, right? It's 2t squared plus t. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent, or just make it a t because that's a constant. So now, to find this, we just have to evaluate it at the upper limit, 4, and then subtract off, evaluating it at the lower limit, 2. And don't forget that this is a subtraction, right? You're finding the big area and subtracting off the little area to get the area in between. Well, 4 squared is 16 times 2 is 32 plus 4 is 36. 2 squared is 4 times 2 is 8 plus 2 is 10. 36 minus 10, 26 meters. And of course we get the same answer. Now I'm starting to think that might have been a little easier, right? If this was part A, if this was all we were doing, right? Might have been a little easier to do the integral. Maybe. Maybe not. Could still find a rectangle and some couple of rectangles and triangles and do it geometrically. But again, just showing here that the calculus, following the rules of integral calculus, right, does work out to be the same as the geometry. But let's do one more example here. In this case, calculus is the only way to do the problem. So here's an acceleration function for an object, which is t squared. This is not a uniform acceleration, right? This is an acceleration that changes as t squared. It's not a very complex function, but it still is, right? More complex than constant. So if I'm going to graph this on a graph of acceleration versus time, what would a equals t squared look like? Hopefully you've done enough math that you know that it would be a top opening parabola with a 0 y-intercept, right? Plug in 0 for t, you get 0 acceleration. Now if I want to know the change in the velocity from 1 to 2 seconds, right, there's 1 to 2 seconds. Well, geometrically, that's that area. Right? The change in the velocity would be the area from 1 to 2 seconds. But this one is not a nice shape. Right? So how are we going to find that area? Well, you could, do the rectangle thing and take the limit as the number of rectangles approaches infinity, which is also known as a Riemann sum, which you're going to love when you do second semester calculus, right? Or we could just use the rules of calculus. We know that the change in the velocity is the integral of the acceleration with respect to time, and in this case, we want to evaluate that from 1 to 2 seconds. So we plug in the acceleration function, don't forget the dt, and now we do the integral. Well, the power rule says add 1 to the exponent, divide by the new exponent. See how I did that? Add 1 to the exponent, divide by the new exponent. And I get 1/3 t to the third, or t to the third over 3, either way, same thing. Right? If you've got a friend that's already had a year of calculus and you ask them to do this integral, right, I mean, they won't even think about it. They'll just know what the answer is, right? And you'll get like that, those of you that are in first year. You just need practice. Same thing as derivatives now, right? And remember, if you take the derivative of this, you ought to get the function back. Multiply by the exponent. 3 times 1/3 is 1. Subtract 1 from the exponent, you get t squared. Hey, look, everything worked, right? So you can always check your answers with derivatives. And now we just have to evaluate it at 2 minus evaluating it at 1, right? Which we can do because we're doing the big shape, right? Which would be the entire shape from 0 to 2, and subtracting off this little shape to 1. Work it through. That's 8/3. That's 1/3. That's 7/3. Couple of sig figs. 2.3 meters per second. Now, I'm not quite sure how you're going to get that answer without doing a whole lot of rectangles, right? Unless you happen to know some integral calculus. So we're going to take some time here in the next few days and do some problems and build on this idea a bit. And we're going to mainly focus on motion graphs and motion functions, right? Acceleration, velocities, and positions as function of time, right? Because I think you can wrap your brain around a little bit more. And then we'll go back in and start using this stuff in energy. Because if you remember here, we have defined lots of things in energy as area under the curves of particular kinds of graphs. That's why I'm teaching you integral calculus right now. So go on and have some fun with the worksheet. If you're brand new to integral calculus, write out steps. Right? If you've already done a year, give me at least a couple of steps so I know what you're doing, right? Don't just write out the answer. That's a little sloppy.